Hello and welcome to another finite elements lecture. In this lecture, we are going to discuss buckling analysis by using FEA. Buckling is one of the most fascinating concepts in solid mechanics, and it has many real-world applications. At the end of this lecture, you will be able to appreciate the importance of buckling analysis, explain the terms critical load factor, and mode shape, set up finite element buckling simulations, and finally interpret the simulation results. So why do I need to know about this? Buckling can cause catastrophic failure. You may know that for structures, we need to remedy for internal forces that are caused by thermal expansion. For instance, we use supports that are called a roller support, which allows for expansion. The tracks that are shown in this figure have been under massive compression, but this was not due to thermal expansion. This was done by an earthquake which brought two cities in New Zealand closer together by 2 meters. The tracks could not accommodate that amount of contraction, and as a result, they buckled. Well, we should know that the allowable load can be reduced if buckling is likely to happen. An example is this tank. These tanks are designed to sustain large internal pressures. However, this tank can buckle under small external pressures, which can be as small as the atmospheric pressure. In the test that I'm going to show you, the vacuum valve have been closed, so not allowing the air to enter the tank and maintain equilibrium. Then the internal pressure is reduced, which leads to buckling or catastrophic failure. Like this. So here I have shown a diagram. On the x-axis, I'm showing the geometrical ratio, which in our case, for instance, it can be the ratio between diameter and thickness of the tank. And on the y-axis, I've shown the allowable load, which in this problem is the external pressure. So this curve has two regions. The static analysis region is when, for instance, the thickness of the tank is big enough or the diameter is small enough that the tank would fail due to the failure of the material under quasi-static conditions or loading. However, when the thickness is small, this vessel could go unstable, i.e. it would buckle, which puts it in a dynamic situation and it will lead to the catastrophic failure, as you saw in the video. Buckling is not always an evil. We can use buckling to design new products. Older keyboards used buckling. An example is shown here. This spring inside the key buckles under the compression and it gives the release feeling under the finger. So essentially the compressive energy in this spring is suddenly changed to bending energy, leading to a reduction in the compressive force. Well, now let's look at a formal definition of buckling. Buckling is loss of stability of an equilibrium configuration without fracture or separation of the material, or at least prior to it. So let's look at our keyboard problem. In this structure, the spring is under compression. As we press the key, the spring is compressed to a point that it suddenly bends, but this loss of stability is not due to the failure of the spring, although it can lead to failure down the line, like the problem that we saw earlier, the pressure vessel problem. So buckling occurs when the stored membrane or axial energy is converted into bending energy, but without a change in the externally applied load. Again, back to the spring problem. Here, when we apply the force, this force gets reduced when the buckling happens, and we do feel that under our finger. It's like a give. under the finger. Okay, now let's discuss the buckling theory by using this example. This is a beam under axial force. This beam is simply supported on one end and it has a roller joint at the other end, so essentially it allows us to expand or contract it axially. The beam is under a lateral distributed load that you can see here, and this lateral load produces deflection. The maximum deflection at the center is shown by VC. This beam is also under an axial load, which we call it P. So when these forces are pointing away from each other, it means that this beam is under tension, and when they are pointing towards each other, this beam is under compression. We can show that the maximum deflection at the center of this beam is a function of QC, and QC is the maximum value of this distributed load. So here is the function that we can find for the relationship. So here you can see that in the denominator we have K, which is the stiffness. We know this is stiffness before when we were looking at beam elements and truss elements, and this is stiffness is a function of the geometry and material properties. We have another parameter here which is actually really interesting. This is another type of stiffness which is different to this one. This stiffness is a function of the axial force P. So this is the stiffness that is produced by the axial or membrane force, and we call it the stress stiffness. So again, let's look at our equation here. In the denominator, we have the overall stiffness, which is K plus K sigma. And as I mentioned, K sigma is a function of P, which is the axial force. So this is actually the same problem. I have a beam that is under axial force. And then when this force is pointing in opposite directions, this beam is under tension, correct? But what happens if we change the direction of the force? What do I mean is that when these forces are pointing towards each other, then our structure is under compression, right? And if I apply this force up to a certain point, we may see that this axial force is now driving the structure into bending, correct? And this bending can be abrupt. Let's look at this problem mathematically. If we increase the compressive force on the beam, this term will be negative and it will just increase in magnitude. At some point, this K sigma will be equal to K, but in opposite direction. So what happens is that you will have a denominator that is zero, and that is a singularity. Mathematically, this is a singularity, but mechanically that does have a meaning. So let's write that here. K plus K sigma equals 0. And by doing so, we can find the value of P that would make these two equal but opposite directions. So P critical, we call it, would be equal to minus pi squared E elastic modulus, second moment of area, divided by L squared, correct? So this is actually really interesting. Mathematically, you have a denominator that is 0, and that would mean that even if you have a very little, very small amount of lateral deflection, you can produce very large, maybe infinite, theoretically, value of lateral deflection. This is buckling, right? As we described, buckling is when stability is lost under this membrane, these axial compressive forces or stresses, and then this axial energy is then, or membrane energy is transformed to bending energy without increasing that axial force or stress. So we can actually plot the deflection, which is V, versus that axial force. So here, just to help us with showing the correlation between these two, showing the relationship, I'm showing P here, but imagine this is P in compression, okay? Not in tension. So here I'm showing the magnitude of the P when it is in compression. As we are increasing the axial force in compression, this beam will contract, the length will be reduced, right? Up to a certain point, which is our P critical. Yes, so the magnitude of this is P critical. At this point, our structure has two pathways. One is to continue to sustain the axial load, correct? Until it fails under static conditions, so the material itself fails under this compression, or it can buckle, which means that it can take another path, which is this one, correct? So one path is this, and then another path is this. Up to this point, our structure is stable, but beyond that point, P critical, it may continue to sustain the compressive force, or it may buckle under the loading. And well, often in real world conditions, we don't have a perfect structure. Always we have some sort of disturbance in the structure, maybe small lateral force, wind, something else, or imperfections in the material itself. So buckling is very, very likely in real world structures. And this is where this is happening. So this point where our structure has to decide which way it should go, and that is called the bifurcation point. So bifurcation means branching. At this point, it can really branch, and most likely it will branch towards buckling. We show that critical load can be defined by this equation. We can show as well that the shape of the beam at buckling would be like this. This is like a half sine shape. We can also show that there are other solutions that would give us the same conditions that I was explaining, where the net stiffness is 0. For instance, we could have this critical value, which is 4 times larger than this one, and the corresponding shape of the beam at buckling would be like this. So this is a complete sine. And so on. So we can have infinite number of loads or critical loads that would satisfy the condition. The shapes that the beams will have at buckling, these are called mode shapes. And we have another definition here, which is the critical load factor defined here. It is defined as the ratio between the critical load and the applied load. Okay, how does FEA solve a buckling problem? In FEA, the K sigma matrix is the stress stiffness matrix for each element, and it determines the stiffness of the element under membrane stresses. This stress, the stress stiffness matrix, it depends on the membrane force and geometry, as we have seen for a beam before. For a two-dimensional beam elements with length L under membrane force P, this stress stiffness matrix looks like this. So here we have the axial force, and we have the length of the beam only. So how this stress stiffness matrix is determined? First, the software will perform a standard linear analysis with an arbitrary reference level of external load and determines this K sigma for that level of load. A good exercise, a good practice is to always try to keep this arbitrary load at a unit level, so it can help later with finding the critical buckling load. Once this K sigma reference has been determined, the software will solve an eigenvalue problem which looks like this, where we have the structure stiffness matrix, we have the critical load factor, and we have this stress stiffness matrix. So essentially it is trying to find conditions, the values for the lambda critical, where the net stiffness of the model is 0. The eigenvector that's shown here is associated with the critical load factor, and it is called the buckling mode shape. As you have seen before, it determines the shape of the structure at buckling. And finally, the critical external load is determined by multiplying the critical load factor by that external load or reference load. So that's why I said that if you use a unit value for this external load, then this critical load factor will be equal to the critical external load, so you don't need to do this manipulation later. Okay, let's solve a problem with software here. This problem can represent common situations in pipelines where pipes are subjected to axial loading due to thermal expansion. So here's the definition of our problem, and at the end what I would like you to determine is whether this beam will buckle before it fails under the load. So what do I mean? I mean that we need to do two sets of analysis. One is a static analysis, another one is a buckling analysis, and then compare the allowable loads from these two analyses and see which one is the lowest and determine under which conditions this beam would fail. So I have a supplementary video that you can go and watch and see how this problem is solved with software. A word of caution here. So far we have certain assumptions when we did all this analysis. We assume that the geometry is perfect, material distribution is perfect, there is no imperfection in our structure. And essentially what we have done and what we have used is the linear buckling theory. So in linear buckling theory, you can see there is a very clear bifurcation point or buckling, critical buckling load that tell us when the structure will buckle. But in reality, our structures are not perfect, so the beam is not straight like this. It might be slightly bent before even you apply the load. So like the demo that I just showed, in that demo, that aluminium beam has been put under that axial for several times and it's already a little bit bent. So the actual geometry could be slightly different to that straight line. And this is the imperfect, right? Imperfect geometry. This one is the perfect geometry. So what happens when you have initial imperfection in your structure? When you're loading your structure, if you have initial imperfections, there will be deviation from this idealized bifurcation path. You will see that there is coupling all the time. There is a bit of coupling between the membrane deformation and the bending or the deflection. This path then would look like something like this, okay? So this is the imperfect path, or the path that is related to the imperfect geometry. So you can see that if we are, for instance, looking at certain amount of deflection in our beam, like here, the pink one is happening before the purple one. Okay, so that would mean that this amount of deflection would happen before even your structure starts the bifurcation or buckling based on the linear theory. In other words, we are, by using the linear theory, by using the relationship to find the critical buckling load, we are overestimating the failure load of our structure. Well, you shouldn't be disappointed because Still, the linear buckling theory is extremely useful. It's being used to have a very good estimation of what loads that should be avoided or what loads can be utilized in the design process. But you can also try to make your predictions more precise after you have had this first pass on your model. You can incorporate the imperfection in the geometry material in your model, and then you can run nonlinear simulations that would give you a more accurate estimation of the response of your structure to the membrane loading. In summary, we have learned about the importance of considering buckling in the analysis of thin or slender structures. We learned about different concepts in the buckling theory, the critical load factor, and mode shape. We have learned how FE packages set up a buckling analysis. Now we understand why static analysis is needed first, because the software needs to determine the stress stiffness matrix first, which then goes into the eigenvalue problem. And we have also learned about the limitations of the linear buckling theory, which essentially what we discussed was around imperfections in the structure, and that the linear buckling theory is very useful to give us an initial estimation of the buckling load. But if we want to have more precise estimations, we need to incorporate imperfection in our structure and do nonlinear analysis, which is beyond the scope of this module. Thank you for your attention.